Hello! So, in this video, we're going to be proving another theorem, specifically if a sequence of continuously differentiable functions, fn, converge pointwise to some f on this ab interval, and the sequence of fn prime converges uniformly to some function g on ab, then we have these two facts. F is continuously differentiable on AB, and f prime of x is really g of x for every x in AB. So this is one of those things where there's a lot of letters and subscripts floating around, so I kind of want to draw just a quick little sketch diagram so you can see what's happening. So we're saying, okay, we have some fn's, right? So we have some fn's that are converging pointwise to some f, right? And these fn's, very importantly, have some properties. They're continuously differentiable, and they're converging, like we said, pointwise to f. Now, at the same time, if we take, so fn's are continuously differentiable, if we take the derivatives fn prime and look at those, now, what you'd want to say is that these things, because those converge, these should converge in some sense. And if these converge, if there's any justice in the world, right, it should converge to the derivative of this thing. Because these go to that, so this should go to the derivative of that thing, right? But, as it turns out, that's not always true. So in the hypotheses, what we're claiming is, okay, we can take the derivative of fn's because we're assuming by hypothesis that they are differentiable. And we are also assuming here that it converges, in fact converges uniformly to some function g that is unrelated in any way-ish to f, right? That's the hypothesis bit, is that we have fn converging to f. If we take the derivatives of fn, which we can do by hypothesis, and we are assuming that it converges to some unknown magical function g, and there's no clear relation between f and g. Okay? What the conclusion, right, the predicate, the end part of our theorem is telling us is that in reality, g is the thing we would want it to be. It really is f prime. Right? So this is the conclusion that we're trying to draw. And it turns out that this is actually really important because it doesn't just immediately follow, because you have fn going to f pointwise, that you can, like, if we didn't know like this part of it here, and we just had, okay, fn is differentiable and it goes to some f, you can't claim then that the derivative of fn's go to the derivative of f. We need this extra piece here that says that they do converge in the first place uniformly to some value, something, then we can make that claim, right? So unless you know that the fn primes already uniformly converge to something, you don't know that these things converge at all, let alone that they converge to the thing you would sort of expect, okay? So the whole point of this theorem, and the reason I'm giving it this long intro, is that it's giving you the condition to do the thing that you intuitively think you could do for free. It turns out you can't do it for free. You need this uniform convergence to something before you can claim that really these things are related the way you would think. Okay? All right. So with that, let's jump into the proof here. So we have a sequence of continuously differentiable functions fn, right? So continuously differentiable means that not only do we have that fn is differentiable, right? I can take a derivative, but those derivatives are continuous, right? So since fn primes are all continuous, and fn prime converges to g uniformly, g is continuous. This is one of our previous theorems that we did in another video. And not only is it continuous, all of these, thus they are all Riemann integrable. This is just a little aside over here. So put that off to the side there. Okay, so the Fn primes are continuous. Continuous things are Riemann integrable. Fn primes converge to G uniformly, which makes G continuous. Thus, G is also Riemann integrable. So we can apply the fundamental theorem of calculus. Now, it's important to note, I didn't write it, but it's important to remember that these things are converging uniformly is what gives me G being continuous and thus Riemann integrable. That's only true on A to B, right? So all of this is only on A to B, regardless of what the actual domain of F, F prime, etc. actually are. So by fundamental theorem of calculus, we have that I can take the integral of the Fn primes of x dx from a to x, and this gives me Fn of x minus Fn of a. And this is true, which is why I just mentioned it a second ago, for all x such that a is less than or equal to x is less than or equal to b, right? All the x in that interval. Okay. So I have that, all these, so I have Fn primes and G are Riemann integrable. Since the Fn primes are Riemann integrable, I can apply FTC here. So then, since we have now this relationship here, we also know, since, again, Fn converges, so since Fn prime converges to G uniformly, I'm going to stop writing it because it's included in this notation. We have, by a previous theorem we've done a video on, I can take the limit as n goes to infinity of the integral a to b of Fn prime of x dx and interchange and evaluate, right? So if I interchange, then I have the integral of the limit of Fn prime, but I'm assuming that that goes to G, right? So that goes uniformly to G. So this is going to just be then the integral a to b of g of x dx. Okay? So if I take a limit up here as n goes to infinity, and I will get then the same idea here, right? So if I took a limit on this side, I would get exactly the same thing. So I'm going to be doing that, but I'm going to do that and take a derivative. So I'm going to take a limit on both sides and then a derivative outside of that. So I'm going to take the derivative with respect to x of the limit as n goes to infinity. So I'm going to write it in the other order just because it helps me chain this out a little better. So this is Fn of x minus Fn of a equals, so that's this, so then I'm going to have it here. So I'm going to have the derivative of the limit as n goes to infinity of the integral a to x Fn prime of x dx. It's an n. But I know that this thing is really just that. So this equals then the derivative with respect to x of the integral from a to, so here, right, the limit is a to b, so I'm replacing b with x. So I have an x here, gx dx. But Here then, I just have the integral and then the derivative is undoing the integral, right? So this is one of the, you learn it in Calculus 2 probably is the second fundamental theorem of calculus. But regardless, whichever way you happen to remember this, these things cancel out. So this would be integrable by the fundamental theorem of calculus. You get the antiderivative of g at x minus some constant. The derivative kills the constant, brings the antiderivative back down. So all that's to say, all you get here is g of x. Okay. On the other hand, over here, what do we get? Well, we have that the limit as n goes to infinity of this stuff. I am supposing at the beginning that fn converge pointwise to f, right? So this is really going to give me then the derivative with respect to x of f of x minus f of a. But f of a, whatever that is just a constant, so the derivative kills that thing off. Derivative of f of x gives me, again, I'm assuming, right, that f is differentiable, and it's differentiable to some f prime then. So I get f prime of x. So in particular, I get that f is a differentiable function, because I've now derived the derivative. And sort of more importantly here is that I get f prime is equal to this, that, this, 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 this. So I get, in fact, that thus f prime of x is actually equal to g of x for any x where I could have put it here. But that was all the x's between a and b, everything I could integrate, right? For every x in a to b. So, strictly speaking, I could have done this without taking the derivative and gotten this equals that, equals that, equals that, equals, well, stop there, then take a derivative to get that, but I just did it sort of all at once. Okay. So again, I want to sort of point out that it's really important here that I know that g exists in the first place. I know that the fn primes do converge to something, and that the fn primes not only converge to something, but it converges uniformly to that thing. That's the only reason, that's the only way I can get this thing to actually sort of go anywhere, to work, right? And it's worth, so as an aside, I'm just going to recall real quick one of the examples we did sort of at the beginning when we talked about pointwise versus uniform. Looking at a really sort of simple example, so if we did something like fn of x is x to the n, right? Then f prime n of x, this is clearly a nicely continuously differentiable function, right? It's a monomial. So this gives me n x to the n minus 1. But, so I can go from here to here. Fn converges to 0 pointwise, but not 0 fully, right? So let me actually rewrite this sort of clearer. It converged to that function that looked like 1 for x equals 1 and 0 for x in 0 to 1, not including 1, right? And so you might try to do something like this, right? Because here I have fn converging pointwise to f. I have that the fn's are differentiable. So you'd like to claim, right? The intuition says that you'd like to claim, so we want, I'm going to write a little question mark here because we don't always get what we want. What we would like, right, what we want is that fn, I put my n in the wrong spot. Fn prime of x converge to whatever this thing is, right? If I make this, call that g, converges to g prime, right? Because I have, right, I would like to say that because I have a thing that I can easily take a derivative of I have that it converges to some thing, so I'd like the derivative of this to be whatever that converges to. But it turns out that's not true. And in fact, it's sort of spectacularly not true, because as n goes to infinity, what does this thing end up doing? This ends up going to some infinite thing. It diverges at 1, and then ends up being 0 everywhere else for the same sort of reason that x to the n was. Or actually, I guess it doesn't even go to 0. It actually goes to sort of uniformly infinity everywhere except 0. So it sort of flips the role here, where it's 0 at x equals 0 and infinity everywhere else, meaning that it's just some crazy nonsense thing. And that's not what the derivative of this thing would look like. That's what the derivative of that thing, as n goes to infinity, taking that, would look like. But, so this is just a little bit of an aside, but at the same time, this shouldn't be surprising, because remember, fn prime certainly is not going to be a uniformly convergent thing, because here, this thing doesn't even have any sort of nice convergence property. I'm missing exactly this, knowing that g exists and fn prime converges uniformly to it. So since I don't even know that g, the thing down here exists, that the derivative that this thing should converge to exists, there's no way I can claim that they're equal, right? So point being that this theorem is giving us a result that a lot of people want to just sort of assume for free without this hypothesis down here, and it is very necessary, and not in any kind of exotic way. I mean, even just a monomial is showing that this can fail, right, with a really nice function like x to the n. So it is really important to remember that you can't just sort of freely go through this square however you'd like. You have to actually have the hypotheses here. Okay? So with that, that is pretty much the end of that. So this is the theorem that tells you when you can actually do the derivatives versus the sequence of functions and their derivatives and how they're all sort of interrelated. All right. And we're done.